All right. Good morning, everyone. Can you all hear me okay at the back? Is the microphone working? Good. Okay, this is fun. It's my first conference since COVID. All right, I'm talking today about Compiler Gym, which is one application of reinforcement learning for systems. So let's talk about why we care about compilers. So we have this problem that compiler engineering is this kind of Sisyphean task. Right? The job of the compiler engineer is never done. The reason for that is that compilers are incredibly complicated. They have lots and lots of moving parts inside them. Modern architectures are incredibly complicated. The instruction sets are difficult and whatnot. So actually trying to figure out how to build a compiler that can squeeze the most performance out of a particular architecture is already a very, very difficult task. But what makes it worse, of course, is that the world is not static and that every 6 months your architecture changes, come out with new accelerators, our software workloads change, our programming languages change, everything keeps moving. And what this means is that we have this problem where we're never able to actually keep our compilers up to date with what we want. We have this gap between the kind of performance that our architectures can kind of offer versus what our software can actually achieve. And over time, that gap, I think, is widening. Okay, so how are we going to make this task easier for the compiler engineers? So let's think of it as a data science problem. Rather than requiring our engineers to sit down in front of a Vim and figure out how to build the perfect compiler, let's treat it as a data science thing. Let's do the standard machine learning process where we're going to collect a bunch of examples. So examples in this case might be particular optimizations that we're interested in. And what we're going to do is we're going to go out into the world. We're going to say, here's a bunch of programs we care about. Here are a bunch of optimizations we care about. We're going to run those optimizations on different programs. We're going to measure them empirically. And then that's going to give us what we would call training data. So something that we could say, okay, for this program, this optimization worked well. For this program, this optimization worked well. And we can bundle all that together, turn it into a supervised machine learning problem, and then learn ourselves a model. Okay, so what's nice about this is that the first thing is that we've taken the human out of the loop. We don't require our compiler engineers to figure out, what is the best heuristic for all optimizations. We've also turned this into an automatable task, so something that we can just keep fresh by every time our architecture or every time our workloads change, we can just rerun this process and keep our compiler up to date. Okay, so what are we going to need to do in order to achieve this? First thing we're going to need to do is we're going to need a way of representing a program for machine learning. So there are a bunch of different techniques that you could do for this. The kind of classic one is you have some piece of code. You're going to say lower it down to some kind of compiler IR, and then we're going to examine that IR in order to produce numeric features. So this could be, we've been doing this for years and years, but examples could be, counting. What's the simplest thing? We could count the number of instructions in the code. We could see, how deep are our loop nests. But there are a lot of different approaches we could take here. This is just one. But once we've got our way of summarizing the program, we're going to collect a bunch of different programs from out in the real world, our benchmarks. And we're going to say for each one of those, we're going to extract the features. We're going to then measure empirically what is the best optimization decision by, let's say we're doing loop unrolling. We could try a bunch of different loop unrollings. And then for each program, we'll have what gave the best performance. And then we're going to give that to a machine learner, supervised machine learning task. And we're going to build from that a model. So a model is a thing that's going to try and infer from those features what is some underlying function. And then our model becomes the heuristic. So the idea is we take that model, embed it inside our compiler, and now rather than relying on a complicated chunk of C++ when we're trying to figure out how to loop unroll, the compiler would say, okay, machine learning model, here's some new piece of code that I've not seen before. Here are the features, and then it will infer some predicted optimization decision. Okay, so that's a very quick overview of just kind of the process by which we try and use machine learning, or one of the ways in which we use machine learning for compilers. So we end up with this system where, you've got a bunch of training programs. We need some kind of driver scripts to run those training programs. We need our feature extractor. From those, we get our training data, which is the optimization decisions and the features. And then we learn our model. So there's quite a bit that goes into it. The good news is that we have lots and lots of studies showing that this actually works remarkably well. If you look in the literature, and you can't see that, it's very blurry. If you look in the literature online, There's surveys, covering there's hundreds and hundreds of papers where we've taken, individual compiler optimizations, we've isolated them, we've shown that you can machine learn a heuristic which does better than whatever is in the compiler. So that's great. So the question I guess we should be asking is why aren't compilers full of machine learning? In fact, if you download your latest Clang or GCC, you'll probably find there's not very much, if any, machine learning inside it. So what's the problem? Well, one of the problems is that actually, in order to do these works, there is this kind of hidden cost, which is it's very complicated to get started in compiler research. In fact, behind each one of these papers, there is typically months of some PhD students' time just getting the infrastructure set up to, okay, so we need a compiler, we need our benchmarks, we need to figure out some way of evaluating all these different things. Doing the compiler infrastructure is not easy. I know because I did quite a lot of that during my PhD. In fact, you typically rely on, in fact, in research labs, it's often the case that if you're lucky, some postdoc, like 5 years ago had some experimental setup that we all just keep reusing because it's too hard to do it every time we want to write a new idea. Okay, so we have the potential for big improvements, but we have this nasty downside, which is that it's very expensive. So that's where CompilerGym comes in, and that's what I'm talking about today. So we want to try and minimize that cost. So what are the kind of challenges that we're interested in? One of the challenges is just how do you talk to a compiler? Like if you're doing some machine learning, typically you're doing this in some Python thing, you might be calling in some high-level toolkit. Compilers are C++, they don't often expose nice APIs for Python, so how do we do that? Next question is, what kind of programs are we going to learn now? So in order to learn a representative compiler heuristic, we need to have a bunch of different programs that cover the space of what we think might be realistic for a human to pass into that compiler. How are you going to measure the reward? So how do you know if you're doing a good job? Maybe you're optimizing for runtime. Optimizing for runtime means you need to collect runtime measurements. Those can be noisy. Those can be actually quite hard to gather in a reliable technique. And then what about just how do you even represent the programs? So there are a bunch of different ways you can represent programs for machine learning. Which one are we going to choose? Okay, so the idea with CompilerGym is it's a piece of software that you can find on GitHub. And our goal is pretty straightforward. We want to make compiler optimization research accessible to everyone. There's a pretty substantial team behind this at Meta. I've had a chance to collaborate with a bunch of nice people, including Yuandong. But more importantly, this is open source. So we have our open source contributors. We've got 3 goals with CompilerGym. What's that movie where the baseball one? Field of Dreams, right? If you build it, they will come. Our first goal is we want to build this toolkit which makes it easy for people to use compiler optimizations for machine learning. The idea being that we want to bring more people into the field. It's kind of been somewhat of a niche field, and we want to expand that. Why do we want to expand that? Because we actually genuinely want the state of the art to advance. There is a lot at stake. Compilers are incredibly important. They're a fundamental part of the computer stack. We know that there are improvements that can be made, but compiler engineer time is a very scarce resource. So anything we can do to improve their life is a good thing. The third goal with CompilerGym is we want to provide some stable benchmark by which, let's say, if you have multiple different sets of researchers all working on similar compiler problems, and those do exist, that they will have something that some shared infrastructure that they can compare their experiments on. Okay, so at a very high level, what CompilerGym looks like is essentially the diagram from Yuandong's talk about the core reinforcement learning loop. So we've got an environment, and an environment in the context of CompilerGym means some encapsulation of a particular compiler problem. Like it could be some LVM tuning problem, it could be it's in GCC, it could be one of the PyTorch compiler optimizations. And what that environment exposes to the user is 3 things. It exposes the observation, which is a representation of the program or the compiler state. It exposes a reward, which is some signal from the environment of how good the code is or how bad it is. And it exposes an action space. And this is some set of optimizations that your compiler supports. And your job as the user of CompilerGym is to write an agent whose job it is to select an action from that action space that would maximize cumulative reward. So just a couple of things to, a couple of implementation details just to pull out. So the first thing to say is that it's, yeah, we built on the OpenAI Gym interface, which is a very simple one. The goal is that it lets people write your agent in Python. It's a familiar interface to people who do RL, and if you're not familiar with RL with that interface already, then it's trivially simple to understand it. It is a Python library. We expose everything as Python types. Like if you're dealing with arrays, you're going to get NumPy arrays. If you're dealing with strings, you'll get strings. We've got graphs. There is nothing specific to, there's no, nasty compiler specific data structures involved. And then the third part is that this is a self-describing interface. So you don't need to know anything about how the particular environment you're interacting with is implemented. You don't need to know how the compiler works. You can ask it from the environment all of the capabilities you need in order to apply reinforcement learning. So it's essentially one giant abstraction between the kind of gnarly C++ APIs that the compiler is typically written in, and the nice, straightforward, high-level, very simple Python API that we want reinforcement learning or machine learning researchers to be able to play around with. Okay, so to show it off, I'm going to just walk through some code. So like this is an example of how you might use it. So like I said, it's a Python package, so it starts off with pip install. There's no custom build scripts or you don't have to do anything fancy to get it up and running. Just Python 3.6, I think. So what we're going to do is we're going to import compiler gym, and that's going to pull in all of our environments, these different compiler optimization problems that we support. And then we're going to say, okay, compiler gym, go ahead and make me an environment. And in this case, if you guys can see that, we're going to say, we're going to use the LVM compiler. We're going to pick a particular benchmark to play around with, let's say a quicksort. We're going to pick this observation space, which is, in this case, that's called autophase. So that's our representation of the program. And our reward signal is we're going to optimize for instruction count, and we're going to compare that against what the compiler does. Okay, so then that goes ahead and in the background just makes you a little environment, and you then interact with that the same way you would any other environment in the gym framework. So you can say reset the environment, and then you can, in this case, what we're doing is picking a random 1,000 steps through the environment. So we're saying, okay, pick me an action, apply that action, give me an updated state. So this being a toolkit for compilers, it isn't, we do slightly extend the APIs. For example, we add things that are useful for compiler people. So as an example, some way to get your code out when you're done with it, so you can analyze your bit code or run it or do whatever you want afterwards. So I just want to talk about why a gym. So a lot of compiler problems map very nicely to reinforcement learning. So it could be, so if you look inside the compiler, they're typically arranged as a big pipeline. So from one view, you've got like a piece of code and it's going through various stages of optimization or transformation. At each one of those stages, you've got decisions about how those, how you're going to apply those transformations. But also even things like the way in which optimizations like inlining are applied is it's typically you're walking through a program, like you're walking through a graph of the program and you're making a decision, which could be, let's say, am I going to inline this function? Am I not going to inline this function? So it's a simple task applied throughout a large piece of code. So we've got this mapping that a lot of compiler problems map nicely to sequential decision-making processes. We picked Gym because it's a nice, flexible and popular, that's the important thing, library. People know it already. If you don't know the Gym framework, I think that previous slide showed almost every method in the API. It's like 4 methods. It's very straightforward. Of course, you don't have to do reinforcement learning. You can use that as just an abstraction for doing your own search or, I don't know, a genetic algorithm, some custom black box optimization, or ask ChatGPT. And the third part is, why not just a big supervised data set? So we're trying to make compiler optimization research simple. So why don't we just release a giant data set of here's compiler optimization stuff? So short answer is we have done that as well. You can use it. You can find it if you go to the GitHub repo. But we didn't just want to, release big labeled data sets, because Gym lets you do things like that we haven't considered. Like you could target optimizations that we haven't thought about. You could target architectures we haven't thought about, or workloads that we haven't thought about. So instead, what we're doing is, we're releasing a toolkit that people can use to make their own data sets. Okay, so I want to go back to the challenges and just enumerate how we are addressing them with CompileGym. So the first challenge: how do you interface with the compiler? We have just simplified it to a Python package install. You don't have to worry about the compiler. What programs do you train on? So what we've done is we've taken the approach of just parceling up and shipping as many open source benchmark suites as we can get our hands on, and those come bundled inside the CompileGym package. So we've got a handful of million of handwritten programs that you can, and also the driver scripts and the validation scripts and all the other stuff. How do you measure reward? So we provide reward signals. So built into it, when you create your environment, you can say, I want to optimize for runtime, I want to optimize for code size, flops. It is entirely environment dependent. And then how do we represent the programs? So we've got several observation spaces. What we did is basically took past published prior works, and we implemented them or imported them inside CompileGym and made them available. So you can just ask for it. You can say, hey, I want a graph representation, or hey, I want that guy's embeddings from that Murex paper in 2018. So an overview of 3 of the environments we ship at the moment in the public release. One of them is LVM. The problem we expose for LVM is selecting and ordering optimization passes. This is one of the classic compiler problems that people have been targeting for, I don't know, decades, I think. Like long before machine learning, we all kind of knew that the task is like, you've got a piece of code, you've got a compiler which contains a bunch of optimizations. Which optimizations are you going to apply to that piece of code, and in what order? It's a massively high dimensional search space. You have to kind of know when you are done. Like your job, an episode never terminates. We support this problem for runtime or for code size. And then this is our most mature problem environment. We've got a bunch of different observation spaces in there. Everything from weird directed graph representations to like simple fixed size feature vectors. For GCC, we've got a command line flag tuning space. Again, one of the classic in computer science. We kind of picked problems that people have already been attacking for a number of years, so that there's good baselines to compare against. It's a huge space, and we have a couple of different observation spaces for that. And then the third environment is perhaps more interesting for those guys who are interested in like machine learning type workloads. It's this very interesting problem. So it's based on LoopTool, which is a machine learning compiler. What you end up with, or what a program in LoopTool looks like, is basically just a massive series of nested loops for doing, let's say, some kind of kernel, some matrix multiplication, or some other kind of machine learning operator. And what the LoopTool environment lets you do in CompileGym is it lets you manipulate those loops, like figuring out how to reorder them, how to split them, how to tile them to get you the maximum throughput on a CPU, and I think possibly GPU. I can't remember. Okay, so a couple of different or a few different environments. I want to give some examples of using CompileGym. So this is targeted more at the systems people, the guys who might not be super confident with ML. So here are some like examples of how easy it is to apply. So in this case, what we're going to do is we're going to say, okay, here's some environment. We're going to use the LVM phase ordering problem. And then we can use a library like RLlib, which is a library of pre-implemented state-of-the-art optimization algorithms. It's got PPO and ActCritic and a bunch of different algorithms that Yuandong mentioned. And because we're using this Gym API, and because RLlib targets this Gym API, we can just say, okay, RLlib, here is some compiler problem. Go ahead and train for me an agent, and you will get for free in literally those, whatever it is, like 6 lines of code. You'll get TensorBoard dashes of, you can see how the thing's behaving and how things are converging and whatnot. And then we say, okay, well, let's say we want to evaluate how important is the different observation spaces. So like we've got different ways we can represent it, different feature vectors. So we can just change this one line and repeat our experiment. And then that figure on the right there shows the effect of observation space on the performance of agents. Or we can say, okay, let's fix the observation space. Let's see how performance of RL changes with different benchmark states. So because we've got a whole bunch of different programs that shipped in CompileGym, you can just say, oh, okay, give me programs from AngerBench, or give me BLAST programs, give me CSmith programs, give me programs mined from GitHub. And then because RLlib is this nice library of, a nice easy to use library where it's got a bunch of different agents implemented inside of it, you can say, okay, I want to try, is Apex better than Impala? Or you can just ask for a different reinforcement learning optimization algorithm, and you're off to the races. Okay, it doesn't have to be reinforcement learning. It's just that Jim happens to be primarily targeted at reinforcement learning folks. Here's an example of where we're going to use Nevergrad, which is a gradient-free optimization library. It's got a bunch of different optimization algorithms inside of it, like GAs and whatnot. So we can say, okay, Nevergrad, here's some problem, or in the vocabulary of Nevergrad, you'd say, here's some function, minimize it. Or you could just, write your own techniques ad hoc. Like if you want to do a greedy search, here is a pretty straightforward greedy search. You want to do something more fancy, here's a hill climber. The idea is you can just use this as your API to try out your whatever idea it is that you want to try. So last couple of things, we bundle a few other goodies along with CompileGym. So one of the things is we've got a command line interface. If Python is scary, you can just use this and and with no code, you can still play around with these environments. You can step through them. You can see how different optimizations affect different pieces of code. This one's quite a useful thing just for doing some like initial exploration. The important thing, or one of the very important things for compiler research, is that we've got validation of correctness for each of our for some of our programs. So that's something that's very important and surprisingly easy to get wrong. Is that when you start poking inside compiler optimizers, you can find bugs and your code will silently start breaking. So we've got these scripts that will just detect those things. And then the final thing is, we've got public leaderboards. If you go to the GitHub repo and if you try out one of our problems and you think you've got a cool approach, submit it there, and we would love to demo it. So a little bit of further reading. We had a paper at CGO last year about CompileGym, which I would recommend. Good paper. There's a tutorial which has some activities you can follow along. We've got some videos, some collab notebooks, which you can just step through. So you can try all this stuff in the browser. Oh yeah, I forgot to mention that. You can use this through collab without having to install anything. And then finally, we've got pretty comprehensive documentation. Let's say documentation that's better than an average for research software, but yeah, it's getting there. Okay, I just want to quickly enumerate some of what I think are the interesting open challenges. So one of the big unsolved problems is representation learning. We don't yet know what the best way is to represent programs to neural networks. As we have all seen in the last year, you can get amazingly far with strings and just passing it if you've got big enough models and enough layers. But we know that within compilers, we've got all these different things. We've got graph representations. We've got compilers are full of their own internal representations of code. We've done some work in this kind of direction, but there's a lot more to be explored. Like there's some really gnarly representation learning problems. How to learn over infinite vocabularies, how to represent arbitrary binary data, how to represent the inputs to code. Like I don't think anyone's actually tackled that one. Programs feed off some input data, and we've got to figure out how to serialize that, how to get that inside a neural network, how to get the neural network to generalize about it. That's a fun area. We've got the problem of navigating very, very large search spaces. So with the pass ordering or with the command line flag spaces, if you're not smart about it and you just, if you wanted to brute force it, they're all impossible. They're all, larger than the observable universe. You need to be clever about it. You need to be selective on which parts of the space you think are worth probing and which parts of the space are worth collecting training data over. Knowing how to plan in very high dimensional spaces is important, because in the case of, let's say, you're learning an inlining heuristic, you might have tens of thousands of decisions to make for a single program. And then finally, sample efficiency. Like when you've got such a large space and you've got so many programs, how are you going to actually learn something in a reasonable amount of time? You know, reinforcement learning approaches have historically been very data hungry, and so can we do better than that? Okie dokie. So that wraps up my talk. I just want to say, yeah, so in summary, compilers are fun. You should all be doing compiler research. It is a fun area. There's a lot of stuff to be working on. We built Compiler Gym to make it as easy as possible for people to get into this area. And Compiler Gym is this kind of batteries included, actively developed piece of software that makes it easy for you to interact with compiler problems for machine learning. Okay, with that said, thank you very much for your time, and I'll take any questions.